Good morning once again. I started the video recording. Do you have any question for me? And do you have any comment, any question on the videos, tutorials? Nothing. Perfect. I would like to remind you that if you want to take the opportunity to make presentations, look at the calendar of our lectures, and it's now time to start, because if you look at the calendar, we are here. It's today, it's March 25th. So as you see, in April, we are not meeting very often. And anyway, there are some lectures that will be skipped. And in any case, we are about half of the lectures now. So it's time, if you want to make presentations, to take the opportunity. Okay. I remind you that you just need to send an email to me, and one person alone, couple of persons, and the topic is at your choice. The only requirement is that it's not overlapping with what I'm lecturing, and you know what I'm lecturing, because if you look at the list of the links, you have already everything available. And the other requirement is that you present some technical content, maybe a case study, etc. And if you want to take the opportunity, as I said, it's time. Okay. We had the last two lectures online. We discussed the risk-based adaptation design, and in particular, we discussed probability estimation, probability definition, and estimation. And I closed the lecture on Thursday with a brief mention to probability distributions. Probability distribution, analytical functions describing probabilities. As I mentioned, we may describe a probability density or cumulative probability. It doesn't matter, because we know that one is the derivative / integral of the other. So it is really the same thing. It's like synonyms. If you describe with an analytical function the probability density or the probability distribution, and the cumulative probability, let me say, better said. So the reason why sometimes we describe analytically probability density, and sometimes we describe analytically the cumulative distribution, is that, as I said, one is the derivative or integral of the other, and sometimes these analytical expressions cannot be integrated analytically. And therefore, if we want to give an analytical expression, for instance, of one distribution, like the normal distribution or Gaussian distribution, which I will now show on the screen, we cannot give an integral analytical function of it, because the integral cannot be computed analytically. So we give the analytical description of the density. But as I said, they are like synonyms. So we didn't make any specific example of probability distributions, but the literature proposes a lot of them. If you go over the web and you look for probability distributions, let me share the screen, first of all. So let's open a Google window. Probability distributions, probability distribution. You find several of them, and let's take, for instance, Wikipedia, and let's see. And probably there are several. Okay, here there is introduction to probability, which you don't need to look at, because we already discussed it. There is also some more here, because I tried, as I said, to make it very simple. But if we go to the list of the distribution, which I'm quite sure there is at the end, let me just see. I'm just browsing to the end of the, and It's not here. Anyway, you will find a list of probability distribution. Very good. So, and you see there are many of them, okay? Beta, Boltzmann, Borel, discrete phase, many. You don't need, of course, to look at all of them. And there is somewhere here the Gaussian distribution, which is the only one that we discuss. Why there are several analytical functions, the literature, why we elaborated several probability distributions. Because the task of a probability distribution is to provide an analytical interpretation of probabilities. And of course, it depends on the specific problem you deal with. So if you want to describe the probability distribution of earthquake intensity or the hazard of heat waves is different with respect to the probability distribution that regulates the flood hazard or the drought hazard. They are different because they are different phenomena. So this is why we need different analytical functions. And as I said, these functions are different in shape. So the analytical form of them is different. And moreover, they contain parameters. What is a parameter? It's usually a coefficient that is included in the analytical relationship. Usually it's a constant. And the purpose of this coefficient is to make the distribution flexible, as I said. So it doesn't change the analytical form of the distribution, but it makes it flexible. So in order to gain a lot of flexibility, we have several analytical formulations, and each of them includes parameters to make each of them flexible, because we need to describe several processes. Probability regulates almost everything. I mean, when there is some uncertainty in something, you need to describe this something with probabilities. So this is why we have several analytical functions. And of course, the good question is, given that I have to deal with a risk-based adaptation design under climate change, what is the probability distribution that I should use? This is a relevant question. In general, keep in mind that the larger the number of parameters of an analytical formulation, the larger the flexibility. So you may prefer analytical formulation with a lot of parameters because they are more flexible. Because the parameters are like tune buttons, something that you regulate, okay? With the same probability distribution, you regulate it basing on your data. On the other hand, to make this regulation, you need data. You understand why? Because if you want to describe a process with an analytical relationship that provides a very good interpretation, you need to tune it. But what is the measure that you use for tuning? It's data. What is the reference for tuning? It's data. It's experiments or knowledge in a Bayesian context where you make the tuning basing on your intuition, on your understanding. You need knowledge, which is like a synonym of data, because data is like knowledge, okay? And what if you make this tuning on the basis of a limited knowledge? What if? The result is uncertainty, okay? When you make this tuning and you have limited knowledge to support it, the result is that the tuning is uncertain. So it may happen that you have a limited database and you make your tuning, and then the database increases and you realize that the tuning was wrong because additional data bring additional information, and then you have to tune it again. So probability distributions sometimes are estimated several times. So what is the moral of this long story that I made? The moral is that more parameters, more flexibility, but more uncertainty, and so the need for more data. So you may prefer something that is very flexible if you have a lot of information, but you may prefer something that is less uncertain if you have reduced information. Less uncertain means less parameters. So you have to reach a compromise. And this is the nice question, the fascinating question. I have to describe climate change. Okay, I need to describe it probabilistically because there is uncertainty. I don't have a deterministic knowledge of climate change. So what is the distribution that I use to describe the future climate? These are fascinating questions. And how to tune it? What kind of information should I use? Should I use the historical information? Should I use some modeling result to tune this probability distribution? It's nice. It's nice, but of course it's something that we have to deal with at a technical level. So we need to understand how to move forward, and we will try to understand. Okay. Good. Now let's forget about this page and let's focus on the only distribution that we discuss, the Gaussian or normal distribution. And don't learn the analytical relationship by memory. It describes the density. And why the density? Because this analytical relationship cannot be analytically integrated. And therefore, it's better if we provide the formulation for the density, which doesn't contain any integral, any unsolved integral. If you are good in mathematics in integration, try to integrate this, and you will see that it's not possible. Of course, numerically speaking, is not a problem. We can use numerical integration, so it's absolutely not a problem. And we did in R already density estimation and cumulative probability estimation for some selected processes. But in analytical terms, this is the density, and we don't have an analytical expression for the integral representation, okay? Or we have an analytical expression, but there is still an integral in it, okay? Good, and why the Gaussian distribution we are discussing? First of all, here is the shape of the density for varying parameters. The Gaussian distribution includes two parameters. Here they are indicated with mi and sigma. I go back to the analytical representation, just 1 second, it's here. So we can put on the screen the two representation, graphical and analytical together. You see that in the analytical representation, there are two parameters, mi and sigma. And this is the result in the image of the tuning. Just 1 second, I have a student in the waiting room. Okay. So this is the result of the tuning. You see different values of mi, different values of sigma give different graphical representation of the density. Here on the horizontal axis, there is the random variable. Suppose that it's river flow or earthquake intensity. And in the vertical axis, there is the probability density. As you see, if I vary the parameters, the shape changes, but there are some characters in common. And one striking character in common is symmetry. They are symmetric around a vertical axis, the vertical axis that passes for the highest peak of the distribution. They are symmetric, and this is the character that is maintained as a result of the analytical shape, even if you change the parameters. And you see that if you look at the parameters, mi regulates the position of the highest peak. So look at the blue curve, mi is 0. Look at the green curve, mi is -2. And you see that the green curve is shifted on the left. Okay, the other curves, but the green, they have the same mi value, the same value for mi, and they have the peak in the same position. And what is the effect of changing sigma? The effect of changing sigma is that the curves become fatter or thinner. Sigma regulates the fatness, let me use this term, of the curve. So the highest sigma is in the yellow curve, which is fatter. And, you know, try to follow me in this reasoning. You may notice that if the curve becomes fatter, then the peak lowers down. This is clear. Why? Do we have any answer of why? Yeah, let's try an answer.
The area under the curve is the same.
Yeah, the area is the same. Okay, it is correct, but somebody else has another interpretation. Your interpretation is correct, but I think we may add something more. So the something more is another question. Why the area must be the same? Yeah.
Larger peak, they have to spread the area. So
yeah, this is correct. So let me go over the blackboard and yeah, the answer is correct. Any other comment? Because I think the answer was correct, but I want to make it more understandable to everybody. Any other comment on that? Okay, good. Let me change the camera. Let's see, I think I can stay here. Okay, and let me explain. Basically, you said area is the same. Area is the same, which is correct. Area is the same. It is correct. And another one said area. I asked why area is the same, and another one said because area is 1. Area equals 1 because P, the capital P, the cumulative probability is in the range, is in the range 0, 1. So let's provide an interpretation for this. We know that cumulative probability indeed should stay in the range 0, 1 for the Kolmogorov axioms, for the definition of probability, cumulative probability. And we know that the probability density is the derivative of probability, okay? So let's compute the cumulative probability depending on the probability density. So I say P of a given value. I don't like this chalk. Just 1 second. Let me try to take another one. Okay, this is short. Shouldn't give any problem. Of a given value of x, this is fine. It's given by the integral of the probability density. And what are the extreme of integration? In the case of a Gaussian random variable, the domain is extended from -infinity to +infinity. So the Gaussian distribution, the domain of the random variable is not bounded. It goes from -infinity to +infinity. Remember, these are real numbers. Otherwise, we wouldn't talk about probability density, okay? And the domain is -infinity, +infinity. So you already understand that if I want to describe river flow, the Gaussian distribution is not good because river flow cannot be -infinity, okay? It can be +infinity, but not -infinity. So anyway, if I want to compute the probability of not exceedance, cumulative probability or probability of not exceedance of a given value, lowercase x of a random variable, I have to integrate between -infinity and x. And I have to integrate the probability density in the x. Okay. And if I want to compute the probability distribution P, probability of not exceedance of infinity, then I compute the integral from -infinity to +infinity of, again, Px in the x. And this is the probability of not exceedance of +infinity. Clearly, it's 1. Because probability goes between 0 and 1. If I take probability of not exceedance of +infinity, which is the integral over the whole domain of the probability density, you see, I span the whole domain from -infinity to +infinity. This must be 1. And therefore, the area below the curve must be 1. And it's the same. Sorry, I made probably a too large step. What is the integral of the probability density? If you see the probability density here, what is the integral over the whole domain? Is the area below the curve, correct? The integral is the area. So the area below the curve, if I extend my calculation of the area from minus infinity to plus infinity, of course, this is a graphical representation. It doesn't go to infinity, but you understand, if I will compute the integral from minus infinity to plus infinity, it's the area below the curve must be 1, okay? 1 here. And therefore, same area below the curve, and the area is 1. This applies to any probability distribution, not only the Gaussian. If you integrate over the whole domain of the random variable, over the whole horizontal axis, for any probability distribution, the area is 1. Okay, perfect. So this is why with a larger, with a fat distribution, you get the peak that is lower, of course. But what if you get a fatter distribution in terms of, in technical terms, okay? Let's talk among scientists, technical scientists, like we are. The yellow card, which is very fat, means that probability is spread over a large interval. It means that I can get a relatively high probability of getting high value and low values. It means higher variability. A fat card means higher variability. A very thin card, like the blue one, you see, it means that the probability is concentrated around 0. And if you just get to -1, -1.5, the probability is close to 0. So there is no variability. The values are concentrated over the most probable outcome. And we are a bit reassured. Think if you are interested in getting protected against future climate, and you see that the future climate has a probability distribution that is very concentrated. It means that you are quite certain of what will happen. Remember that probability also describes uncertainty. So if you have a probability distribution that reduces to one line, it means that you are certain of the future. If the probability distribution is very fat, it means that everything can happen. So of course we are concerned about variability. And in fact, we started our conversation together. We started the subject by discussing change and variability. And we said we have to distinguish between them, because variability, in any case, it's similar to change, but the solutions are different. The solutions are different. But in terms of, if I am concerned by climate spikes, by climate outbursts, variability, change, they both can give spikes, can give unexpected values. Okay, change may give in the future unexpected values, but also the yellow curve, you see that it may, with a relatively high probability, may produce outbursts, high values. So variability, in terms of effect, is similar to change, but the solutions are different. You understand why? Okay. One thing is getting protected to something that is very high, but it's constant in the future. The future is like the past. So I study the past to cope with variability. I can study the past and assume that the future will be similar, because variability means that it's not change. Change means that the future is different from the past. So it's clear that the solutions are different. Okay, in terms of the Gaussian distribution, the two parameters describe indeed the mean and the standard deviation of the random variable of the process. The mean is the most expected value. The mean is also called expected values. And the mean, you know what is the mean, okay? You know how to compute the mean of a series of numbers. And the result is the most expected value. So me here is the mean, and sigma, which quantifies the variability, as we said, it's the standard deviation. If you don't remember what is mean and what is standard deviation, just look in Google, standard deviation, and you see how it can be computed. It's a measure of variability. Standard deviation and mean. Again, if you don't remember, it may happen at the exam that you get questions on the standard deviation. So just be sure that you know what it is. Okay, this is a very trivial concept, but trivial concept, but it's trivial, but it needs to be studied. So you need to study what is if you don't know it. You will see that it's very simple. Okay, also the computation is very simple. In R, you have a function called SD, which means standard deviation, to compute the standard deviation of numbers. And if the numbers are constant, the standard deviation is 0. Okay. Okay. So the Gaussian distribution, we said, it's not really a good distribution to describe natural processes, environmental processes. Because the domain is from -infinity to +infinity, which is something that, you know, several environmental processes, the random variable that describe these processes are bounded at 0. Many of them, not all of them, but many of them are bounded at 0. And another thing is the shape of the tails. The Gaussian distribution is symmetric. Typically, environmental processes have one tail that is longer than the other one. You know what is a long tail, because we did it in the computation of the Po River. We noticed that the probability density of the Po River flow has a long right tail. So typically the tails in environmental processes differ. Okay, good. So what is the reason why I mentioned the Gaussian distribution? Just one distribution and I mentioned the Gaussian. You could say, yeah, if we cannot use it, why don't you mention a distribution that we can use? I mentioned the Gaussian distribution because it's also called the normal distribution. And you may wonder, why normal? Why? Okay. And it's indeed a very important distribution because there is a theorem, which is called the central limit theorem, which you don't need to learn. And this theorem is a well-known theorem in statistics, proves that no matter the random process that you describe, maybe intensity of earthquakes, maybe floods, maybe, no matter the process, so just select something random, okay, described by a real variable, real random variable, and try to aggregate it by computing the average of these numbers describing the process over time windows of increasing length, okay? Like, for instance, river flow. You have daily data. For the Po River, we use daily data. Try to take the monthly average. In R, you have ready-to-use functions to compute the average over any window, okay? So try to compute the monthly average, which means average every 30 days. Try to compute the annual average, which means average of 365 days. And unfortunately, we cannot because we don't have enough data. Try to compute the 10 years average. So as you increase the window, the average converges to this distribution. So the central limit theorem says, no matter the process, if you average over increasing over window with increasing width of any random number, you get to the normal distribution. This is interesting. It is interesting because it means that in any casual process, there are some rules. Indeed, this is trivial. It is trivial because we know that even tossing a coin, which is the the most typical example of a random process, there is a rule. The rule is that you get a probability of 0.5 of getting an head and probability of 0.5 of getting a tail. So it's clear that any causal process has a rule. But this kind of rule is a bit astonishing because it goes to the detail of describing the probability of any single number, and the fact that any causal process, just by increasing our perspective, we widen our perspective and converges to a so specific probability distribution, is a bit interesting. Is a bit interesting. Because it applies to any causal process that you may think of. So it's indeed, and this is why we study this distribution. Okay, good. Any question? Now, there is an interesting consideration that I want to make to close this lecture dedicated to risk-based adaptation design. Now that we know probability, let's know how to estimate probability. Let's go back to the very simple, trivial risk equation, which is here. Okay, this is our equation. Let me open the PowerPoint because I want to get it very large over the screen. I think I don't have the PowerPoint here. Strange. Okay, sorry for that. Let me go back to the beginning and let's make it larger in this way. Okay, so remember that risk is given by the product of probability, vulnerability, and exposure. Probability, we call it also hazard. Okay, and remember what is vulnerability, what is exposures. I just want to remind you them because, first of all, these are very basic concepts, and probability, I don't need to repeat what is, okay, and just take into account that here usually you see the capital P. We use probability of exceedance, okay, in the risk equation. We use probability of exceedance, and keep in mind that the lower the probability of exceedance, the lower, and the higher the intensity of the event. So think of a big earthquake, or think of an earthquake with a very small probability of exceedance. It's very large, okay? An earthquake with a large probability of exceedance is a normal earthquake. I mean, something that happens quite frequently. Okay, and what is vulnerability? Vulnerability is the degree of protection. The degree of protection, which is varying from 0 to 1. And what is exposure? It's the damage if the event occurs, the event of probability P occurs, and let's suppose that vulnerability is 1. So the city gets flooded. What is the damage? Okay. And damage in most of the cases is expressed in economic terms, in economic units. So it's not bounded in a given range. It's bounded in the range 0 plus infinity. This equation, first of all, tells you one important thing. Let's think that, let's consider the application of this equation to study a climate change problem. Where is the effect of climate change here? It's in the probabilities, in the hazard. After a changing climate, the same city with the same degree of vulnerability, the same degree of exposure, gets a higher probability of getting an event, a flood, an earthquake, okay? So climate change affects P. Now let's suppose that P changes. You see that in terms of risk, a change in P has an effect on the risk that depends on vulnerability and exposure. And this is a key concept. Climate change, the impact of climate change, the risk may be defined also as the impact of climate change, depends on the local conditions, on the local exposure, local vulnerability. Suppose that you have a climate change and exposure is 0. What's the problem? Okay, the land gets flooded, the exposure is 0. It means no value, you are not concerned. Your priority must go where exposure is large and vulnerability is large. Or let's suppose that you have a land that has an high value, but it's fully protected, it's fully resilient, okay? This term, resiliency, means that the land is protected. Resilience means capacity to recover. Of course, if a land is protected, the capacity to recover is larger. So if the land is resilient, vulnerability is 0, your priority against climate change should go to other locations. Remember, we are talking about adaptation to climate change. So we are accepting it. It's a different story if you are concerned by climate change and you may say, I am concerned anyway, even if the land has 0 value, even if because I am concerned by mass extinction, which is global. This is another story. We are talking about adaptation here. Adaptation, remember, means that we are accepting climate change. We are accepting it and we dedicate our resources to adapting to it, limiting the risk. This is why we are talking of risk-based adaptation design, okay? So local conditions in adaptation, of course, means a lot. Now, it's interesting to have a look at this equation because vulnerability depends, it's not a constant here. Vulnerability depends on P, because a city may be protected against an event of a given probability, but not against an event that is larger than that has a lower probability of exceedance. Can you follow me? Lower probability of exceedance means a larger event, a more intense event, okay? Remember, lower probability of exceedance means larger than that is almost impossible. So huge flood, huge earthquake. So vulnerability depends on P. And in which way? It's interesting to make a kind of consideration. And exposure, you may think, no, exposure doesn't depend on P. Indeed, there are several studies which show that exposure depends also on the probability, because think of a flood, a small flood. Okay, small flood means large probability of exceedance. Okay, if the city gets inundated, only a small part of it gets inundated. So the exposure depends also on the extension of the inundation. If you get a huge, what is called a mega flood, it means that the whole city is inundated. So also exposure depends on the type of event and therefore depends on probability. In which way? It's interesting to think at it, because you are interested in the max risk. We are interested in the max risk. And therefore, the question is, what is the combination of these 3 factors, probability, vulnerability, and exposure, that brings to the max risk? This is interesting. So I propose to study this relationship between these 3 factors in a graphical manner, because I think it is easier. So I go down, because the last figure, this one, is the graph that I want to discuss with you. Let me just 1 second. Okay. Here, I think that even with the label of the privacy setting, no, just 1 second. Okay, now it's on the screen. Let's make a comment on this graph. First of all, let me just be, self-promoting. This graph was it's an idea that I had because I like the graphical representation. I like the graphical analysis because you know, it's a kind of in Italian we say the formazione professionale. It means a professional limit, and I am an engineer, and therefore I like the graphical analysis. But on the other hand, I also got this graph reviewed by several colleagues, and they confirmed that it's not wrong. So let's look at this graph. First of all, what is in the horizontal axis? It's the intensity of the event. And I wanted to write intensity of the event because I didn't want to put it probability, okay? Probability, and I didn't want it, I wanted to use this more narrative approach. So the intensity of the event. Of course, as you move along this axis in the right direction, you get an event that is more intense, which means lower probability of exceedance. Okay, as I move right on the horizontal axis, the probability of exceedance goes down. And the return period goes up. If you want to use return period, remember that if we say that P star is probability of exceedance, so if we say that P is probability of probability of not exceedance. So prob no, sorry, but there are some chalks that cannot really be used. I don't know how to say in English when you have a chalk that when you use it over the blackboard, you get like, okay, okay. In Italian we say fa schermire, okay, and I don't know how to say in English. Okay, this is probability not exceedance. No. Like when you pass with the nails over the blackboard, you know. Okay, and let's call P star probability exceedance. Okay, and T is the return period. T return period. Okay, T is equal to 1 over P star, or it's equal to 1 minus P. Okay. So when the intensity of the event goes up, the return period goes up, and the probability of exceedance goes down. Okay, so this is the horizontal axis. The event may be any type, okay, earthquake, flood, drought, whatever. On the horizontal, on the vertical axis, I have exposure, vulnerability, and risk. So let's call into play these curves one by one. And okay, let's consider first of all the vulnerability curve, the red one, okay? As the event increases, what happens to vulnerability? Vulnerability, up to a certain extent of the event, up to a certain intensity, is zero, because, for instance, the city may be protected by a levee against a flood, and unless the levee gets overtopped, vulnerability is zero. So up to the overtopping is zero. So I may expect that vulnerability is zero up to a certain extent of the event, and then it goes up. It goes up and reaches the value of 1 for a given intensity. And the shape of this increasing phase, it depends on several things. It depends on the socioeconomic context. It depends on the type of the event, okay? So don't think of the flooding. The flooding is something that okay, we can also think of the flooding. Suppose that the levee gets overtopped. It means that the levee is destroyed suddenly. So you have a part of the city, at least a part of the city that is inundated. So for instance, for this intensity, you have a vulnerability, which is here maybe 0.1, because the levee gets destroyed and a part of the city gets inundated. Okay. And then, for instance, if you think of an earthquake, some of the buildings may be protected against huge earthquakes. Some other buildings may be protected against lower intensity earthquakes. All the buildings are protected up to a certain minimal intensity. So when you get here, every building is protected up to this earthquake intensity. Any building is protected. And then the earthquake intensity increases, and you have some of the buildings that collapse, other buildings that remain standing up. And therefore, vulnerability is the fraction of the building that is destroyed, for instance. It depends on how you measure it. And vulnerability may be quantified in different ways, of course. You may count the number of people that are killed, for instance, over the total population, so the proportion of killed people. Or you may count the proportion of buildings that collapse after an earthquake, and you don't care about people inside because you have reasons for not caring, not because you don't want to care about people, but because you may have reasons. So it depends on how you measure vulnerability, okay? And therefore you have this increasing pattern, and you wouldn't expect any decrease of vulnerability because it's monotonically increasing, okay, the function. It's continuously increasing up to reaching the value of 1, okay? Now, let's talk about exposure. Exposure, same thing, up to a certain extent of the event, even if vulnerability is 0, you may have that only the floodplain is flooded, and in the floodplain, you are prepared for the flooding, you don't have any damage. But then, as the inundation starts to cover a larger area, you get increasing exposure. Okay. Perfect. And keep in mind that there are increasing exposures with a shape, with a pattern that depends on the socioeconomic context typically. Okay. Keep in mind that there are studies that proved that with decreasing vulnerability, you have an increase of exposure. So suppose you build a levee. The levee, people feel safe, like, oh, great. Now I'm not flooded anymore, so let me invest in this area. So vulnerability decreases, exposure increases. What is the result? The result is that if you get an exceptional event, the risk is larger with respect to no levee. This has been proved, for instance, around the Po River. This is clear. After the levees were increased, the value, the exposure of the land increased a lot. After the altitude, the level of protection of the levees has been increased, means lower vulnerability, and the exposure increased a lot. Okay, now let's focus on the yellow curve, which is the risk. It's the product of probability of exceedance, which is decreasing with increasing intensity of the event. Okay, probability of exceedance is decreasing as I move right on the horizontal axis. But vulnerability and exposure increase. But the combination of the three may usually, typically, it depends on the patterns, of course, but typically may lead to a max. And then there is a decrease. Because you understand, for a large intensity of the event, vulnerability and exposure don't increase much more, while probability goes down, probability of exceedance goes down, and therefore you may get a max risk. And typically in risk-based adaptation design, we are interested in getting protected against this max risk, because it is the max expected damage. This is the situation corresponding to the max expected damage. Of course, you may say, why don't we get protected against everything? Because first, it is not possible. If you think about climate, you cannot get protected against anything, against everything, because climatic variables typically don't have a max. So if you think of an extreme wind, extreme storm, there is not upper value. So if you want to get protected against any possible outcome, you should get an infinite value of wind velocity, an infinite precipitation depth. There is no max value typically. Second thing, you may not have the resources, and the environmental impact of a protection, you understand that it's maybe large. Think of a flooding. You need maybe a huge reservoir upstream in order to get protected against a very huge flood, and the reservoir is impactful. Think of a levee. You cannot make a levee like 100 meters high, because where do you find the material to build up the levee? You generate a great environmental impact if you take gravel, or not gravel, because a levee is not made by gravel, but the clay from other locations to build a huge levee. It is generating an environmental impact. It is costly. We may not have the resources. So it is fully justified that we try to identify a compromise. And the compromise is located in the max risk. And you understand at this point how it's important to estimate probability reliably, how it's important to estimate vulnerability and exposure. Finally, there is a but here. So let's suppose, okay, we locate the max of the risk, and we get adapted to it. This generates a consequence that we are not interested in what happens in the extreme right of this graph. So once we located the max risk, usually we forget about what happens here after the max risk. This is a known effect. In risk-based adaptation design, we try to forget about extreme, very extreme events. In fact, if you look at the legislation for flooding, for instance, suggests that we get protected against floods with a 200 years return period. This is a European rule, 200 years return period, which means a precise probability. The European rule doesn't say like 1,000 years return period. So we usually forget about it. So if we are suggested to make our design, because the rule says that, against a certain probability, 200 years return period, why should we care of what happens for larger return periods? We forget about it. So I am self-promoting again. So what if something which we believe it's impossible happens? Okay, and this is a very simple article to read. It's still under review, so it's something that may change, and it's very easy to read. But basically, what this article says is, think of the flood in Florence in 1966. It was something that was really unexpected. People didn't think of it, and why they didn't think of it? Because if you make your design according to this reasoning, which is not new, I mean, it is a classical approach of the engineer to locate the max risk and make the design against it. So you forget about what is, you think it's impossible. If the legislation says your design event has a 200 years return period, I mean, you think that everything exceeding that, it's like impossible. People think it's impossible. And then you get the unexpected event. The unexpected event, which is located after the peak of the risk, and it's located somewhere here. And what happens? So what is the moral of the story? The moral of the story is don't forget about what happens here. Try to estimate, especially your exposure, the progress of your exposure in the far right of this graph. So it may happen that your exposure, and here you have the return period, T, it may happen that your exposure, like we see here, it is 0 up to a certain extent, and then it goes up, and then like in this graph, basically it gets to a plateau. But it may also happen that after the plateau, you get something like this, okay? And you don't realize it. You don't realize it because maybe that your max risk is here, okay? And therefore you say, okay, I forget what happens here. And maybe that you are in a similar situation. And therefore, if you get an event that is really impossible, you get a huge, maybe a larger risk, a huge damage, especially if you measure risk in terms of loss of lives, for instance. Maybe that you make your design basing on economic risk, but you don't consider other ways to measure risk, like loss of lives. And then you may get the real big trouble. And there are several examples of such big trouble. And like, okay, I said Florence 1966, but I can mention the flood in Germany in 2021, the flood in Libya in 2023, and there was another huge flood last year. I don't remember where. Sorry. While I'm talking, and I mean there are several examples several examples of impossible flood, and therefore the question is, but if they are deemed to be impossible, how can we find several examples? Maybe climate change. Because maybe that here, the scale of the horizontal axis has changed after climate change. Maybe climate change, maybe also land use change. I mean, climate change is not only, it is not the only reason. It's not the only possible reason of an impossible flood. And these causes are discussed in this article, like the impossible flood may be caused by climate change, may be caused by land use change, several other issues. But I mean, these changes imply a change of scale of this axis. You don't see it in the graph. You should redraw the graph with a rescaling of the horizontal axis. And indeed, if you look at this paper, there are several. This is an example of the flood in Germany. And you see, impossible, the flood in Germany of 2021. But I will show you another graph at the end of the paper. And look here, the measurements start from 1945, okay? And you see, this is impressive. And okay, here a description of various risks, and here are the reasons why impossible flood occur, and there is environmental change here. Environmental change includes climate change. And this is, again, the flood in Germany, but the record is extended. Look, 200 years ago, a similar flood. And this highlights the importance of data, the importance of memory. Okay. And look, the flood in Germany was believed so impossible that really the problems that occurred with the flood were something of really astonishing. Like in an hospital, they lost the power and they had to carry the patients downstairs manually because they didn't have any protection against any backup solution, any power generator. They couldn't use the lifts. So they were not really prepared against that. Now, here in the article, you see something similar. Yeah, this is the risk equation. It is formulated in terms of density and not in terms of cumulative probabilities. So it looks like different, and there is an integral. When I teach, I prefer not to use integrals signs because for clarity. And here there is a similar graph to what you are seeing over the blackboard, you see. And it is similar. Return period instead of intensity, and that's it. And this is the case I was mentioning over the blackboard. Exposure that increases a lot after a certain return period. Okay, good. So this paper is a reading for you, but not to study. If you're interested, you may have a look. How to find it? It's online. It's open access. So if you just keep in mind sword, Damocles, flood, you find it over Google, okay? And if you add my name, it's even easier. And it is, as I said, an easy reading. It's not really, there are two equations, and the equations they are the risk equation. Okay. Any question? Yeah.
You have mentioned that with lower vulnerability, the higher the exposure will be.
Yes.
Because of this safety net does.
Because
but in the graph with increasing vulnerability, the
yeah.
exposure is increasing. How is it?
Yeah, because the pattern the pattern depends on the local condition. Here, this kind of effect is not considered. Okay, is not considered, and therefore, but indeed, is not explicitly considered, because you may see that you may see here that the pattern of exposure probably is possibly determined by the pattern of vulnerability, and here is not highlighted in detail. But maybe when I made the computation of exposure, the computation of exposure is depending, for instance, on the number of buildings, and maybe that the number of buildings was determined by the progress of vulnerability. And if you want to learn more about this kind of, which I'm not mentioning explicitly in the lecture because I didn't want to add too many details, but if you look in Google for Levy effect, this is a well-known effect, and for instance, this one, the Levy effect. Okay, if you look at these, let's see the images. Yeah, okay. This is the image that I wanted to find. This is an explanation of the increase of exposure after decreasing vulnerability. You see here that there is no levee, and the buildings are far from the river. And here with the levee, the buildings are getting close to the river. One second, because I saw something that was quantify the interplay between the construction and etc. So there are several papers that you may read. Okay. What I wanted to say is this kind of Levy effect was observed in Italy along the Po River already around 1950s, 1960s, because after the big flood in 1951, the level of the levees along the Po River was raised 1 meter. So they put 1 meter more. And they observed already in 1960 with the economic boom. You know, the economic boom was the great period of economic explosion after the Second World War, which was favored by international agreements on the rate of exchange. I mean, after the war, the countries made an alliance in order to sustain each other in terms of economy. And therefore, they fixed the exchange rates of the different currencies through an international regulation. And this allowed the economic boom, stimulated the economic boom. And they observed during the economic boom along the Po River a great increase of exposure after raising the levies. So it is a phenomenon that was described in textbook in Italian already when I studied during my degree, so already in 1990s. And then it was discovered at the international level 10 years ago. And there were a lot of publications. If you remember in Google, when I searched for Levy effect, a lot of recent publications in the last 10 years. And this is something that happens quite frequently in science. You have sometimes the national literature that may anticipate 100 years development that at the international level become known after, as I said, 100 years. And 100 may be too much, but in this case, it's not 100, it's like 60. But in terms of statistics, the Russian literature was 50 years ahead of the international literature because the Kolmogorov was Russian, the Russian statisticians, already in 1930, 1940, they conceived methods that were discovered at the international level around the 90s, after 50 years. And this is why, this is because the national literature sometimes doesn't get an international diffusion, especially in the past. So Italian literature was not known at the international level. And then 10 years ago, there was an Italian researcher, like a PhD student, a little bit older than that, that basically translated in English. I am simplifying things. It was not just a mere translation, but it was basically a proposition at the international level of concepts that in Italy were already well established. And it is curious because in science, sometimes you see that indeed people are reinventing the wheel. Sometimes it happens quite frequently because, you know, also in the academia, in the scientific world, you need, in order to make your career, you need to prove that you are able to make discoveries. And sometimes people stimulated by making discoveries, and nowadays with so large literature, sometimes you see concepts that after 10 years are reinvented, and it's interesting. But indeed, sometimes we are reinventing the wheel. Okay, now I think risk-based adaptation design, we can stop here. Questions? Other questions? Okay, good. Now I think we can go back to our list and select the next link, sustainable management of water resources. This is more narrative, and I think we anticipated something already. Just 1 second. I make just an exploration, just 1 second, of what we already did. So don't follow me in this very quick exploration of what we already did, because I think I am overlapping a little bit with something that we did already. 1 second, and not here. Okay, I think it was, okay, this lecture which I suggested you to study by yourself, I think it was here. Anyway, I think a small overlap doesn't harm in any case. Okay, so let's now make a focus on management of water resources, which is one of the big issues related to climate change. And this is the purpose of the next lecture. Here I have the PowerPoint, just 1 second. Okay. Okay. Let me go back to the, sorry, to the web page for a second. Good. Okay, why we discuss about sustainable management of water resources? Because there are huge implications of climate change on the water cycle. And the water cycle is basically an essential component of the climate system. And the water cycle is also essential for socioeconomic development and for sustainability. Indeed, there are several sustainable development goals that are related to the water cycle, to water resources management. And we talk here of management of water resources. So we are not talking about flooding, coastal flooding, river flooding, which are other risks that are related strictly related to the water cycle. The water cycle plays a fundamental role for the sustainable management of water resources, and water resources are traditionally considered a local problem, but actually they have a global dimension. And sustainable management of water resources is heavily affected by adaptation. So it's really a field where adaptation is very important. And this is why we discuss it. And first of all, I want to focus over this figure, and I go back to the PowerPoint, which describes the distribution of water in the Earth system. I think I already showed to you this graph, but I want to make a more refined discussion now. First of all, this is a static picture. Let me anticipate that. This is a picture of storage. It's not a picture of flow, okay? And we will see that when we talk about water resources management, flow is important. But this is a picture of storage. So volumes. Volume means storage. This is, let's call it fixed water, okay? So first of all, a first consideration, there is over in the Earth system, there is enough water for everybody, even if we imagine a situation where the population over the Earth increases like 10 times an order of magnitude, water wouldn't be the main problem. Okay, there is water for everybody. And of course, much of the water is salted. And let's look at the left column. First, another premise before I discuss the first column on the left. The other premise is water is conserved. So unless a scission of the molecules of water happens, which is something that it's unlikely and we don't expect, unless until there is an atmosphere that protects the Earth by cosmic rays or something that could indeed provoke the indeed break the molecules of water. Unless this happens, and we exclude that it may happen, water is conserved. Okay, maybe the quality is impacted. Maybe the quality is worsened, but the volume of water is conserved. So I don't remember the number, which can be easily found. These numbers of the total volume of water available in the Earth system have been estimated like like 50 years ago. I remember the percentages. So 97% is salt water, and oceans include 96.5% of the total volume of water. And then other saline water, which may be included into brackish areas, make a 1%. So you see that about 97.5% it's water that cannot be directly used for human consumption. The fresh water is only 2.5%. Still, there is enough fresh water for everybody, still. And even if the human population increased of a great size, fresh water would be enough for everybody. The problem is the spatial and temporal distribution. So sometimes we have periods with too much water and periods, drought periods, with too less. And we have areas. So when we talk about period, is the temporal distribution in time. And also we have areas, and now we are talking of distribution in space, where there is a lot of water, and areas with no water at all. And moving water is extremely difficult. Okay, we talked because water is heavy, unfortunately. Water has a huge volume because there is a lot of water, and it's heavy. And therefore, you cannot move water like you move gas. You cannot move water in a pipe from Sweden to Spain. This is not possible. You cannot move water from Russia to the center of Europe like we were used to move the gas. The gas, you can move it with a small pipe. If you want to move water, you should build up a huge pipe. You would need a lot of energy because in order to move the water, you need energy. And this is not possible. So you may move water in short areas. Typically, aqueducts serve small regional areas, but they don't usually pass mountains. There is a reason for that, because it takes too much energy, and it requires infrastructures that are impossible to build. So water cannot be moved. We discussed the virtual water trade, which is another way of moving water. But if we talk about physical water, and not virtual water, cannot be easily moved. Okay. So spatial and temporal distribution are a problem, and they are also the reason for international conflicts, because in several cases we have rivers marking the boundaries, and when you have rivers and not mountains marking the boundaries between countries, the share of water is generating international conflicts. There are several examples like the Jordan River, and another example is the Nile River, with the tensions between Ethiopia, Sudan, Egypt for the use of water. Because in the case of the Nile River, it's extremely interesting. People upstream the Nile River, there are Ethiopia and Sudan. Downstream there is Egypt. And now you may have heard that the construction of a huge dam in Ethiopia generated international conflicts, because the huge dam basically keeps the water upstream. It's the Millennium Dam, if you're interested, keeps the water upstream, and then downstream you have people downstream suffering from this upstream usage. So we need international agreements in order to regulate the usage of water. Okay, and now let's focus on the middle column here. The middle column is a zoom on fresh water. So you see that the graphic here, there is a line connecting fresh water in the left column with the middle column. So freshwater, middle column, glaciers and ice caps keep about 70% of the 2.5% of fresh water. Groundwater keeps 30%, and surface water is 1.2%. Which means that, you know, glaciers and ice caps typically is water that we cannot use. So what we can use is about 1/3 of this 2.5%. So it's about 1% of the total water in the Earth system. Now let's zoom over surface water. Why we zoom here? even if it's a small percentage, because it is extremely important for human use. So let's zoom. We have still a 70% that we cannot use, ground ice and permafrost, and then a 20% of lakes. Rivers is only 0.5, 0.5 of 1.2 of 2.5%. And then there are soil moisture, atmosphere, living things, etc. Rivers are comparable to living things. But actually, rivers are extremely important for human use, extremely. So how can we explain this huge importance in terms of total volume that is given to people? Rivers are comparable to groundwater, comparable. So how to reconcile this difference in percentages with this alleged by me importance? Because for the very reason that this is a static picture and doesn't consider flow. So this 0.49% of rivers comes with a static picture. Into rivers, you don't have much water stored, but this water is flowing. It means that the volume, the total volume in one day is not only the volume that you see over the static picture, because this volume is continuously used and replenished, continuously used and replenished because of the flow. So in terms of usage and in terms of climate change adaptation, flow is extremely important. Why groundwater then is less dependent on flow? So why rivers, I said, give to humans a volume of water that is comparable to groundwater? And I said, because rivers are flowing, but also groundwater is flowing, but with a much more limited velocity. So rivers, the velocity of a river, if it is very slow, is like 0.3 meters per second, 30 centimeters per second. Groundwater may be 1 millimeter per second. So the flow is much more reduced. And this gives to you this figure. I think it is highly informative, but in terms of volumes, not in terms of flow. So you have also to consider flow. There is also to say that when water is flowing, the quality is usually better, because the water is continuously changing. In fact, when you take water from a spring, you are a bit concerned if the spring is very slow and just a drop every 2 minutes. And you are concerned if you see water running, you are more reassured, because it depends on the quality depends on the flow. And if you get a contamination, it is washed up, the contamination, much more quickly. Groundwater flows very slowly. And this is why we are concerned by contamination of groundwater more than in rivers. We know that rivers can recover in 1 day or 1 month. Groundwater takes years. Why? We are avoiding to bring sewer systems into a lake. Usually in the coastal areas, or in the coastal areas of lakes, they don't bring the wastewater even after treatment into the lake. Usually they bring it downstream in the river flow, in the river downstream. They don't bring it into the lake. Why? Because we know that the water in the lake flows very slowly. It's like static water, and a contamination takes a very long time to recover. So we don't want to contaminate lakes. We are more willing to release wastewater into rivers because we know the capacity of recovery. Another consideration, an indicator of water quality is temperature, and we know that water flowing is colder than the water that flows very slowly. The colder the temperature, the better the quality for water. So, I mean, also let's take into account flow. And now let me go back to here. Now, so what are the solutions in order to solve the problems in water resources management? First of all, the problems are caused by distribution, by an uneven distribution of water in, as we said, in space and time. So what kind of solutions then can we use, can we adopt in order to cope with this uneven distribution? Okay. First of all, let's consider the distribution of rainfall. The distribution of rainfall basically tells us how water is distributed. Water depends on rainfall. When you have a lot of rainfall, where you have a lot of rainfall, you have a lot of water available. And where you don't have any rainfall, of course, you don't have any water. And here is a global map of a global distribution of monthly rainfall. Keep in mind, I think I already mentioned to you that on average, the precipitation over Earth is about 1 meter per year. And indeed, if you look at the green areas, the green areas is more or less, if you look at Italy, the average precipitation over Italy is 800 millimeters per year, so it's close to the global average. Indeed, if you look at Italy, you see that the color is between green and blue and light blue. Light blue corresponds to about 3 millimeters per day, which is about 1 meter per year, 1 meter per year. And so this is your order of magnitude. If you look at the dark blue areas, it's where we get more rain, and the dark blue areas is about 6 millimeters per day, which means about 2 meters per year. Indeed, the areas in the world where we get the largest precipitation are in the tropics or in the mountains, and it's about 2 meters per year. By the way, in Italy, the largest precipitation, annual precipitation, is in the Friuli region, and it's about 2 meters per year. So this is the distribution that we need to understand in order to identify the areas that are more, that have more water resources, and the areas that suffer more. Let's make the break now. 15 minutes. Do you have any question? No. Okay. Okay, just a reminder that we don't have a lecture next Thursday because it's on Wednesday the Easter break starts, and we will see each other again next Thursday. Okay, it's April 4. Yeah, I think April. Yeah, 1, 2, 3, 4. Okay. So. Global distribution of rainfall, as I said, and look at these are monthly rainfall, and look at the areas where there is the highest concentration of precipitation, because these are the countries that are richer in water, which it is also this water availability is what stimulates and moves the virtual water trade. And it also moves what is called land grabbing. Land grabbing means that there are countries which have limited water resources availability, which tend to buy lands in the water-rich countries in order to cultivate food, to promote agricultural production, and in order to import food at a convenient price, at a more convenient price. And this is a kind of virtual movement of water, which is, of course, engined, fueled by water resources availability. Of course, this distribution may be affected by climate change, even if, in terms of long-term rainfall, so monthly and annual rainfall, we still don't see huge changes. Keep in mind when you look at climate change that the evidence of climate change is different depending on the variable that we consider. So one thing is to look at temperature, and another thing is to look at the water cycle. The evidence that we have is increasingly available for and increasingly supporting a change in the short-term rainfall. So we get indeed additional data and model simulations proving that in terms of storms, of rainstorms, there is indeed an increased risk, while in terms of long-term availability of water, we still don't see big changes. And so when we talk about water resources management, it's not the short-term rainfall, it's not the rainfall with the short duration that is inducing concern, but rather the concern is originated by changes in the long-term rainfall. And as I said, here we still don't see clear signals, so it's still not yet clear how climate change is impacting the drought risk. Even if you get from the media increasing concerns reported, actually the evidence is still not clear. Because, you know, an increased temperature implies also an increased evaporation. So in certain locations, we observe rather an increase of long-term precipitation rather than a shortage. But still, I mean, this is evolving. It's under evolution. And also the prediction by models don't really show a huge change in drought risk so far. Okay, in order to better understand this distribution, nice support is the recently development map of global climate classification. This is the most referenced map of climate classification, and it's called the Copenhagen Climate Classification. This classification has been modified recently, but in essence, it's unchanged with respect to what you see here. It's derived by putting together data on rainfall and evaporation, because of course another another dominant climate variable to determine water resources availability is evaporation or evapotranspiration, which is the merge of evaporation from liquid surfaces and transpiration by plants. So if you look at this map, let me just zoom it out a little bit. You see here in blue the zones where we have more water. In red, the zones affected by water scarcity, and in green, the intermediate levels. So red means aridity. Aridity, as I said, estimated by subtracting evaporation from precipitation. And blue means tropical climate with a lot of rainfall. And tropical means around the equator, as you can clearly see here. It's not necessary that you learn the single climate types, but if you are interested, there is the link here to the Wikipedia page, which explains, gives to you details about the legend. The legend is clickable. So this is AF is tropical rainforest climate or equatorial climate, for instance. If you look on the red, it's the desert climate or arid climate, and you see that for each click in the legend, you get the map of the distribution over the globe of the corresponding climate. The dark green here, it's okay, let's click here, DFC. This is the subarctic climate, subarctic climate. It's a continental climate with long cold winters, and you see the distribution. So it's an interesting reference if you are passionate about climatic distributions. As I said, you don't need to learn this for your exam, because this is something that is too much detailed for our interest. 1 second. Because, 1 sec, okay. Perfect. An interesting reference for you, a comprehensive picture of water availability and distribution is provided by the Aquastat database of the FAO. This is indeed an interesting database, and as the name suggests, Aquastat presents statistics, data about water distribution. And if you look at the databases, which are publicly available, and for instance, country statistics. Let me see. It's a bit articulated. Data analysis. By 1 second. Database. Takes some time. A lot of data to upload. Okay. Let's close this. Okay, this is an example. There are also maps. There are also maps that can be derived here. So you see the variables, in this case, it's pressure on water resources, area world, but you can also select single countries. And for instance, let's look at the first one, Afghanistan. You see that it reports the agricultural water withdrawal as percentage of total renewable water resources. Renewable water resources means the water resources that are replenished after use. And its agricultural water withdrawal is 30%. Freshwater withdrawal as total of renewable water resources is, so it means that they are using 31% of their renewable water resources in Afghanistan. Industrial water use efficiency and irrigated agriculture water use efficiency, etc. Water stress, it's in percentage, and if you want to get details on on single indexes. There are references here that you can, how water stress is computed. There are references that you can consult. Water stress can be defined in several different ways. Typically, it is computed depending on the percentage of freshwater withdrawal with respect to total renewable water resources. But actually, I'm not sure this is the way in which it is computed here. So, but there are references in the database for everything. And this database is what is used to compute here this map, for instance, of total renewable water resources per inhabitant in a given year. This map is quite old already. It's already 9 years old. Of course, we don't expect big changes in the time span of 9 years, but still, in the FAO database, you can get the updated map. And the updated map, if you play with the database, you can get it. Sorry, let me check. You can get it from here. And I think it's something, let me see. No, share, download. It is something here. It's a while that I don't consult it. It was very, very immediate, but I don't want now to make it now because it's not our direct focus. But if you're interested, you can get these maps. Just 1 second. And this one is in particular important because it's the total renewable water resources per inhabitant. So it's the total per capita. And you can see here what are the countries that, in a way, even if maybe in some zones can suffer from, like Australia, from water scarcity, still they have a good per capita water availability. It is interesting to see the country distribution because, as I said, we cannot move water far away, but still within a country, usually they have the means in order to compensate the distribution. And maybe through transportation of water, through organization of support for the people that have less access to water. So within a country, usually at the national level, it's relatively possible, relatively easy to make a compensation. At the international level, there are additional problems that arise, as you can understand. And there are other maps, proportion of renewable water resources withdrawn. And this is something that is interesting because even if the water resource is renewable, if it is withdrawn, and with withdrawn, we mean that we don't use only what is available at that time, but we also use storage. Given that this is referred to renewable water resources, the storage is assumed to be replenished. But still, when you use storage instead of using only what is readily available, it means that you are exposed to a certain risk. Because this storage, it's not clear in some of the cases how long will take to be renewed. So think of groundwater. If we use groundwater, indeed we use part of the storage. It's renewable. This is for sure. Groundwater is by definition renewable. On the other hand, it may take a long time to be renewed. And in some of the cases, we don't have the means, we don't have the technical possibility of estimating the recharge time. Therefore, when we use groundwater, a kind of a light should be turned on in our mind, like this is potentially a risk, because we are not sure that it's readily renewed. If we take water from a river, this is not affecting storage because we know a river also don't have storage. So it's a different story. So when it's possible, we prefer to use water from rivers. And in fact, if you see the dark red countries are those countries which are more concerning in terms of groundwater usage because they are massively using groundwater. And in particular, you see in the Middle East, there are countries where there is a massive use of groundwater, which is maybe not sustainable, even if by definition it's a renewable resource, still maybe not sustainable, this kind of use. And there are several concerns at the global level for this. And how it's estimated, the groundwater storage. So how can we, in a way, assess whether a groundwater usage is sustainable or not? This is a big question. And it's a question that is also related to climate change because under environmental change in general, we are shifting towards a more intensive use of groundwater. What is the reason for that? The reason is that surface water resources are more easily contaminated. It's true that they can be more easily recovered, but they are more easily contaminated. So, for instance, starting from the 20th century, the previous century, we started using more groundwater because rivers got contaminated and the rivers passing through cities. In the far past, we were used to get water from rivers passing through cities because usually cities, okay, Bologna is an exception, but usually cities are built around the river. But then when the river got polluted, then people started to use groundwater. Now we are recovering water from rivers, but still groundwater quality is generally better than the water quality of rivers in the lowlands. If we look to the mountain regions, usually the mountain regions have a very good water quality into rivers, even better than groundwater quality in the lowland, which is in turn affected by fertilization. So there might be a concentration, an increasing concentration of nitrates or phosphates. And therefore, in mountain rivers, we have a better quality. But in the lowlands, when it's not possible to get water of good quality from the rivers, we started to increasingly use groundwater. And for the case of the Middle East, these red and dark red areas, they started to use more groundwater because in some of the rivers, water was retained upstream in huge dams. Look, for instance, at the countries around the Nile River, okay, where Egypt is using, as you can see, a large amount of water resources withdrawn, which means groundwater, because part of the water is now retained upstream. So how can we estimate if these uses, especially you see in the Middle East and in the north of Africa, of withdrawn water resources is sustainable? It is a big question mark because we cannot estimate how much water is underground. The volume cannot be estimated directly. We can estimate, we can observe water levels, but the water level is not a good indicator of groundwater volume. Recently, there has been a lot of research activity which tried to estimate groundwater storage through estimation of gravity changes. I try to better explain. Through satellites, we can measure, so we can get a global map of gravity changes. Gravity is continuously changing, so we know the average is 9.81, but there are local changes. It's not uniform everywhere. And typically, gravity is determined by the mass of the solid mass of the Earth, but also the liquid mass. So it's determined by local mass of the Earth. Water is heavy, so if we take water from the underground, we expect that gravity, if there is a depletion of groundwater volume, we expect that gravity decreases. And indeed, we can find in those countries where you see the red and the dark red colors, we can find in those countries a decrease of gravity. Still, we cannot associate this decrease of gravity to a decrease of mass of water, decrease of volume of water in the underground. We can say that the groundwater storage is decreasing, but we cannot say how much water is there and therefore how long this will be sustainable. Also, climate change, given that is responsible for shifting of seasonality in some countries, is causing an increase in groundwater extraction. I try to better explain with the example, the very clear example of the Po River. The Po River flow is determined also by snowmelt. With global warming, snowmelt is anticipated, so we get more water during winter and less water during summer. Even if the average flow of the Po River is basically unchanged, we can clearly observe, and you can see also in the data that I gave it to you, if you look at the monthly values, you can clearly observe in the past 20 years an increase of April flows and a corresponding decrease of July flows. So this kind of shift in seasonality implies that during summer you have less water. And a possible solution, which we will discuss together, is increase of storage. So I build an artificial reservoir, I store water in April, more water in April, to release this additional water during summer. This is fine. This is a possible solution. Another possible solution is to cope with the water scarcity in July is to use groundwater. And this is what we are doing so far, because in the Po River, recently, in the past 20 years, we didn't increase much the storage. What we did in order to cope with the summer droughts is using groundwater. And it's not clear, even in the Po River basin, if this use of groundwater is sustainable. You understand the complexity of the problem, because if it is true that we are using fossil water is expected to take like 2,000 years in order to recover, and therefore you understand that at a certain point we could get into a situation that is critical in terms of groundwater availability. Okay, this is the water withdrawal per inhabitant, which shows to you what are the countries that are consuming, if you want, more water. And of course, you can clearly see here, in some of the cases, a relationship with the gross domestic product. And in some other cases, you can see a relationship with the climate, because of course, where the climate is warmer, we are expecting the use of more water. And in some of the cases, you can also see a direct relationship with the industrial development, because industries are using less water than agriculture. So where the economy is primarily based on agriculture, you expect a larger water usage. In general, countries with reduced water availability are not the richest one. In general, there is a linear correlation between water resources availability and gross domestic product. And if you look at the FAO database, you can see the data, gross domestic product and water resources availability, and you see generally a very good correlation, unless there are some climatic conditions that prevent agricultural development. Like if you look at Russia, Russia has good water resources availability, very good, but the gross domestic product is not very high because they cannot practice agriculture extensively as they can do in the United States or we can do in the west of Europe for obvious reasons, climatic reasons. But in general, you see a tight correlation between water resources availability and the gross domestic product. This means that there are some countries which, by definitions, they have more resources, and we know this. Okay, we know this. On the other hand, it clearly shows that this, if we don't cope with this disparity, especially in the modern period, where I mean, it's the globalization makes communication, makes also the exchange of goods easier. If we don't cope with this disparity, of course, we have to expect international tensions. Of course, it's clear. So there are some belts around the world which are more lucky. And then there are bands where there are less resources. That's of course it's an effect of the distribution of resources in general. Water is one key resource, but there are other resources. And if we don't cope with this disparity, we have to expect, of course, international tensions, and this is logic. And this brings to our attention the complexity in a period of globalization where the world is becoming more connected. Information is more easily spread. We have also to find new ways, new solutions, and climate change adaptation is one of them, or climate adaptation in general. We have to find more new solutions, innovative solutions to cope with disparity. And this is also the reason why we are becoming increasingly concerned by equality, diversity, inclusivity, and it's because we want to avoid international tensions, international conflicts. Okay, and this is the total proportion of water withdrawal for agriculture. So you see a confirmation of what I just said. Russia has a huge water withdrawal, and huge water availability, but not for agriculture. And you see instead what are the countries that use more water for agriculture. You see countries in the Middle East, and this information, these data are interesting to analyze, and it looks like some obvious results, but actually there is increasing information that is becoming readily available in terms of global information, like this FAO database. And there are several other databases that became available in the past 2-3 years. And I think there are interesting opportunities for putting data together and visualizing a global picture of disparities of socioeconomic conditions, information that are essential in order to cope with the global challenges. And so don't assume that these data are something that is already known, completely used, and not innovative. I think there is room for your creativity if you gain some skills in finding data, in visualizing data through geographical information systems, GIS. There are interesting opportunities for thesis and for other further developments, and for developing innovative ideas. Okay, and now let's talk about, this is spatial variability. You know, when you show a global map, refer to 1 year, 2015, this is spatial variability. There is also the issue, as I mentioned, of temporal variability. And temporal variability means also seasonality. This is a picture of Europe showing, this is a scientific contribution. And I was one of the co-authors, but my contribution was not very much extended over this. It's a contribution that was exploring seasonality in European rivers. And the seasonality means monthly river flows for a river. When we talk about seasonal regime for a river, it means monthly river flows. And you see that there are huge differences. Even in Italy, there are huge differences. If you look at the Alps, you have the max in July in the summer. If you look in the south, you have the max in winter. And if you look at the central part of Italy, the Pianura Padana, and it means our region here, you can see that the river flow has generally two peaks, one in April and another one in November, October, November. And this distribution, this changing distribution over time is also a problem. You may understand, it's quite obvious, that resolving an uneven distribution over time is easier than resolving an uneven distribution in space, because the uneven distribution in space can only be resolved by moving water in space, and moving water in space is difficult. Moving water in time is easier because it means that you have to store water during the water-rich season and release the water during the dry season. So when I mentioned the Po River, and the Po River climate change has originated a seasonal shift, I said, with additional storage, we can solve the problem. Which is true. I mean, for a given river, what is the purpose of an artificial reservoir? An artificial reservoir has the purpose of leveling out the outflow, leveling the river. And now I change the camera because I'm making a drawing over the blackboard. Leveling out the variability in a river. Sorry. Too many clicks. This one, okay, this works. Let me see. It's not really. Okay, I think this is the best. So let's suppose I am drawing one of these graphs. Let's suppose that you have this distribution in time of monthly flows. So let's suppose that let's refer to our region here. So we have a minimum during winter, first max during the season, and then something like this, okay? Okay, this is months. And this is average flow. Usually we indicate the river flow with the variable Q, and here the bar indicates the average during the month, okay? So this is expressing variability. It's showing variability, a minimum and two max. And the area below here is the total annual volume of water resources, okay? The integral of the monthly flows over time gives to you the annual amount amount in terms of volume of water available. Okay, so what could be, if I wanna draw the annual average here, it will be something around, let me see if I make the annual average here. Okay, it's around here, I think. This is the annual average, okay? The annual average is the ordinate of compensation of this diagram, so that the area that is below the annual average should be identical of the area, identical to the area that is above the annual average. So I drew this compensation line by taking care that what is above is more or less in terms of area identical to what is below. So the purpose of an artificial reservoir is to transform this natural regime in this artificial regime. Ideally, an artificial reservoir should have a capacity allowing us to transform the natural inflow in an artificial outflow from the reservoir, which is constant. This is the ideal purpose of a reservoir. Actually, sometimes we don't want it constant because we want more water during summer and less water during winter. But let's suppose for now that we want a constant outflow. The constant outflow is generally what we want for a water supply system. Usually for civil use, not for agricultural use, but for civil use, we have the same water consumption along the year. So we want to transform this inflow into the reservoir into this outflow. And from this diagram, you understand that what is the storage that I need? It can be computed. It cannot be visualized here, the storage of the reservoir. So this is, again, the ideal reservoir. Variable inflow, constant outflow. And you need some storage because the reservoir has to accumulate water during this period, to accumulate water during this period and release water during this period here, okay? And what is the storage that is required for making? This is a nice question which we cannot visualize directly here, okay? So this is a possible solution. On the other hand, you understand that this solution is generating an impact. You need an artificial reservoir. And keep in mind that today, when you propose to riparian people, to people living along a river, to build an artificial reservoir, the vast majority of them is against. Is against because it's a change. It's a change, is bringing some risk, is bringing an environmental impact. In general, keep in mind that people don't like change. People, including us, we don't like change, okay? When we see something changing, in general, we don't like it because it is causing a change in our everyday life. It brings benefit on the one hand, but not for everybody. And it brings also an impact, some perturbation, not for everybody. So in general, we are concerned. In general, we tend to think that if something is changing, it's changing for the worse, not for the better. And this is in general what you find in people. So building a reservoir, it's something that usually it's not accepted, especially in a democratic setting like we are. It's with all the limitations that we know, and I'm smiling. It's still a democratic setting, and in a democratic setting, you have to listen to people. And if you listen, you cannot decide from the top if people are against. And or I mean, you can do that, but it requires a strong political action, and it implies an impact. So if a chief officer who has been elected, takes a decision that is against the will of the population, in principle, an elected parliament, in an elected system, this can be done, because if a person is elected, of course, provided that the action is legal and is complying with the legislation, it can be done. But the impact is that at the next round of elections, people are not re-elected. So this means that in practice, even if it's possible, a top-down decision, usually in a democratic system, it's very hard to be taken. And therefore, I mean, even if the problem seems like an easy problem, I just need a reservoir. As a matter of fact, it's very unlikely that we succeed in building a reservoir. And I think we can stop here because I want to talk further about solution. But I give you an example of a reservoir that of a couple of reservoirs that are highly debated. Or let me just, if you are interested, just search in Google, and this is in Italian. I'm sorry because the literature is in Italian. Diga di Vetto, and you see a long story. This is a dam that the first project was 1865, almost 150 years ago, the first one. They started building it twice and still is there. And this is the last entries you see, it's about 2 months ago. It's public debate, polemic, a lot of videos, and etc. It's interesting. It's very interesting to see what could be the eater of a huge infrastructure. Questions? No ones. Okay. Okay. So see you Thursday online, April 4th. Okay. Enjoy your Easter break. Okay. Try not to study too much. Okay. A little bit, but not too much. And tanti auguri. Thank you.